Welcome back. We are moving into our final unit on recursion. Full disclaimer about recursion. I wouldn't teach this if it wasn't part of the subset. I'm not the biggest fan of recursion, but because it is in the subset, we're learning it. One of my favorite aspects about recursion when I was first learning this myself or learning how to teach it is this quote coming out of the Big Java textbook. The call pattern of a recursive method looks complicated, and the key to successful design of a recursive method is to not think about it. This is going to be hard to teach. It is kind of hard to teach because there's not a lot of content here. There's not really syntax per se. There are techniques, there are patterns that kind of occur with recursion, but ultimately recursion is a replacement for iteration, loops. And so it's not necessary. You're going to struggle to kind of see why we would even talk about it, why we would even learn it. But there is good reason. Recursion is an alternative to iteration, loops. Any code segment that uses loops could use recursion or vice versa. Okay, so these things could swap in and out. Now, I have a theory that because I and we learn iteration first, that we tend to like iteration a lot more. If we had learned recursion first, there's a possibility, I have my doubts, but there's a possibility that we would like recursion even more than iteration. To me, iteration is a little bit more natural in the thinking process, right? Just how I logically work through problems tends to favor iteration. But let's dive deeper into recursion. Recursion, simply put, period, end of story, is when a function or a method, a procedure, calls itself. This is recursion. Here I have my method, and then it's going to print off hello world, and then it's going to call my method. Well, here's my method. It's going to print off hello world, and then it's going to call my method. Well, that's going to print off hello world, and then call my method. The code segment on the previous slide will produce infinite recursion, as a recursive call stack never terminates, right? This just goes indefinitely. My method is calling itself over and over and over again. Okay, some of us accidentally did this whenever we were coding with inheritance because we wrote a toString method that called toString, when really what we wanted was the toString coming out of the parent class. In Java, infinite recursion will invoke a stack overflow error, a runtime error. And yes, this is where that error comes from. This is where the website name comes from, Stack Overflow. Essentially, if this keeps going, it's going to run out of memory because unlike iteration, recursion causes a call stack. You have this method call on top of itself, basically building up, and it's trying to reach an endpoint. But if that just never happens, then it ends up, you just have all these calls to my method taking up the allocated RAM. And then you run out of memory, which is the stack overflow error here. It is a runtime error, right? So there is nothing syntactically wrong with this method calling itself over and over and over again. The error will occur at runtime when you run out of memory, allocated memory. While there is no true syntax to recursion, recursive methods tend to follow a similar format. Okay, so here I have our little example method. We have if some statement, and we're going to refer to this as the base case. We're about to talk more about that. Maybe perform some action, some ending, some stopping action. Otherwise, perform some other actions and do this recursive call. In order to prevent a recursive method from producing infinite recursion, a recursive method should define a base case. A base case is a segment of code, usually an if statement, that represents the simplest entity in a problem set. More importantly, the base case terminates the recursive call stack. While a recursive method can define multiple base cases, only one base case will execute in a given recursive call stack. Defining a base case is not enough, as you actually have to approach it. Okay, so we're going to have some type of base case, some type of little check that we perform at the beginning of the method, right? And if this is met, we're going to perform some actions that will likely stop our recursive function from calling itself again, right? Notice that the call to itself happens in the else, outside of the base statement, outside of the base case, I should say. So this, in theory, the base case, should represent the simplest entity in the problem set. We'll talk more about that in just a moment. But more importantly, for sure, is it stops the recursive call from happening, right? It's just going to basically cause your call stack to collapse. Only one of those is actually going to be executed. You can technically like define more, right? We could have an if, else if type of situation where it's actually multiple entities, multiple base cases that are possible. However, only one will execute, because once you hit one of those, you kind of stop the recursive calls from forming a recursive call stack. And so everything just kind of collapses. So defining a base case is not enough. You actually have to approach it in order to terminate. I think a lot of this is going to make a little bit more sense if we just dive into some code. So what I want to consider is a very popular recursive method, which is computing in factorial. So we have a precondition here that n is a non-negative integer, and we're going to do factorial. So we take in our integer n, and we say if n is 0, return 1. This is our base case. Not only is it going to cause our recursive call stack to stop, this is the simplest entity in the problem set. What do I mean? When we're talking factorial, n being 0, that's the smallest entity in the problem set. If this is not true, right, we're going to basically hit what would be an else, where we do n times, and then we see our call to the method factorial. This is the recursive call, and it's going to start to form a call stack. So factorial is a recursive method. The reason being, it calls itself. That's all it takes to be considered a recursive method. The highlighted text is an example of a recursive call, a method call that is responsible for causing a recursive call stack. N equals 0 is the recursive method's base case. This represents the simplest entity in the factorial problem set. That is, 0 factorial is 1. Whenever this is true, the return statement is executed, causing the recursive call stack to collapse and terminate. Right? Notice that we're only going to do one of these. Right? A lot of the times it's going to be factorial calling itself, calling itself, calling itself. Eventually, this should be true. If this is false, right, if n equals 0 is false, the recursive step is executed. So if this is false, we're going to do the recursive step. Simply put, this is every statement that is not part of the base case, including the recursive call. So notice that in our recursive step, there is the recursive call. Each subsequent recursive call will add code that needs to be processed to the recursive call stack. A stack is exactly what it sounds like, a type of structure in which the last element or process to be added is the last element or process to be added is the first to be processed or executed. Last in, first out. So visually, you think of a stack of papers, right? I'm going to put a paper, a paper, a paper, a paper, right? It stacks up. When I go to look at this stack of papers, the first one I'm going to look at is the one on top. It was actually the last one to be added. And then the next one, and the next one, and the next one, and the next one, on down. That is where this naming convention comes from. It is a stack. The analog to this, maybe not analog, the opposite of this kind of is a queue. First in, first out. Okay, let's step through a factorial example to see how recursive call stack is formed. This is probably going to be the most informative part of these slides. Let's say we do factorial 3. So n has a value of 3. First thing we're going to do is ask, is 3 equal to 0? Well, that's false. So I'll skip over this. We're going to return 3 times factorial of n minus 1. Okay, so that is 3 times factorial 2. Well, I don't know what this is yet, right? I have to go in and figure out what this value is before I can finish doing this multiplication. So let's step inside that recursive call. We're going to ask, is 2 equal to 0? That is false. We'd skip over this. We hit this return statement. We hit the recursive step again, where we're going to take n, which is currently 2, times factorial of 2 minus 1, or just simply 1. Once again, I don't know what factorial 1 is, so we would have to step inside in order to figure that out. We're going to ask, is 1 equal to 0? That's false. We'd skip over this. We're now here. We're going to do 1 times factorial of 0. I don't know what factorial is either. I can't evaluate anything until I keep processing these. So factorial of 0, I'm going to step into that. Is 0 equal to 0? Yes. This is our base case. So we're going to enter the body of the if statement that simply says return 1. This is the height of the call stack, and this is what I mean. We have been adding up. Now, I know it's visually kind of going down, but things are stacking up. I can't process any of them until I basically hit the base case. So this is the height of our call stack. I can now start solving everything. I know what factorial of 0 is now. It's 1. So this means that I can solve factorial of 1. It is 1 times 1, or 1. I can now solve factorial of 2. It's 2 times 1, or 2. I can now solve factorial of 3. It's 3 times 2, or 6. And that's how it worked. That's how it works. Notice that the last call to be added to the call stack is actually the first one to be processed. And then we can actually work our way backwards and finish it out. The factorial method is an example of tail recursion. Tail recursion occurs when the recursive call is the last statement in the recursive step. Hopefully, I'll go back and show it. So here is our recursive step. The last little part of it is the recursive call. This is known as tail recursion. The counterpart to that is just non-tail recursion. We don't have like a good word for it, but this is tail recursion. In practice, methods that employ tail recursion are the easiest to rewrite iteratively. I believe we've done factorial. We have done factorial before. We did it in CSP when we were first learning loops, and it wasn't terribly difficult to write it, and it's not terribly difficult here, right? So the tail recursion is easy to write iteratively. That doesn't mean that tail recursion is bad in practice, merely that non-tail recursive methods are justifiably recursive. So if I have a method that is not tail recursive, so the recursive call is somewhere in between, we're going to see one in just a moment. Those are much harder to rewrite iteratively. You can do it. Everything that can be written using recursion can be written iteratively and vice versa. Let's look at an example of a recursive method that has statements after the recursive call. So something that is not tail recursion and specifies a void return type. So this is also a little bit extra. We saw return statements and factorial, but it's possible to do tail recursion and actually have a base case where we're not returning anything. Maybe we're printing instead. So here I have this make-believe method here called mystery. Let's step through it. Let's start with a initial call to mystery 3. Okay, so a 3 comes in here. We're going to ask, is 3 less than or equal to 0? Well, that's false. So I'll skip the else. And first thing we do, we have mystery n minus 1. Well, that's going to trigger a call to mystery 2. That SOP, it's got to wait. I need to finish doing this call before I'm going to come back and finish out this initial mystery 3 call. Let's step inside of mystery 2. We're going to ask, is 2 less than or equal to 0? No, I'm going to hit this else. That puts another call onto the stack. Mystery of 1. I'm going to go ahead and step inside of mystery 1. We're going to ask, is 1 less than or equal to 0? Nope. Mystery of 0. I'm going to step inside that call. We're going to ask, is 0 less than or equal to 0? Yes. This has triggered our base case. We're going to print out the current value of n. And inside of this call, n has a value of 0. You notice in my console here, I'm kind of showing that off. Now, these other method calls, they still had SOPs that were waiting to be processed. This is the height of my call stack. I can start collapsing the call stack, that is kind of peeling things off the top, if you will, and finish processing the rest of them. So let's go back to mystery 1 and pick up where we left off, which is right here with this SOP. Inside that call, mystery has a value of 1. So I'm going to print off that 1. We're now inside this mystery of 2, where it has an SOP we need to do. Inside of that call, n has a value of 2. So I'm going to print off that 2. And finally, mystery 3 still had code to be processed, so I'm going to step inside of that and print that off. This is what we would actually get. This method is not using tail recursion. Here is, I would say that the else is the recursive step, but the recursive call happens actually before some remaining code. Okay, so the point of this is a non-tail recursion method. This would be a little bit harder to rewrite iteratively. You can do it, but that transition isn't pretty. Let's practice some recursion. That's what a lot of this unit is going to be, because like I said, there's not a lot of content. There's not a lot here to actually learn, but we can get it in a lot of practice, fortunately, because coding bat. So I'm going to head over to coding bat. I'm going to look for the recursion 1 section under the Java tab. And we've kind of already done factorial, but let's look at bunny ears. It says we have a number of bunnies, and each bunny has 2 floppy ears. We want to compute the total number of ears across all the bunnies recursively without loops or multiplication. They have to say this here because this is as easy as multiplying in practice. What do I mean? Well, bunny ears, when we have 0 bunnies, there are 0 bunny ears. When we have 1 bunny, there are 2 bunny ears. When we have 2 bunnies, we have 4 bunny ears. We could literally just do return 2 times the number of bunnies, and we would get an answer. But that's not the point. Okay, we want to start thinking recursively. And this becomes difficult to me because I feel like it takes a little bit of time to get in a recursive mindset and start thinking recursively. And when it comes test time, meaning AP exam, you got to be able to switch back and forth because one problem may be dealing with loops. The next one may be dealing with recursion, and you got to be able to, on the fly, so I'm going to fix the green. I know I'm late on that. You got to be able to swap back and forth. Okay. So we got to start thinking recursively. I would maybe start with the base case. The base case is the simplest entity in our problem set. And for us, that's when we got no bunnies. Okay, so if bunnies is 0, that's my base case. I'm going to return a 0. Okay, so let's start thinking about the recursive step. What we're going to do is return 2 plus bunny ears, passing in bunnies minus 1. Okay, I'll end up tracing this. I hope this works. I just did it off the top of my head. Okay. Now, you just saw me solve one with multiplication, and yet here I'm using addition. Simply put, we basically are going to have two ears for each bunny. And because this is just decrementing by 1, each of these calls represents 1 bunny. Okay, so let's trace this and on this notepad, sorry. And what are we looking at? We're going to, let's start with an initial call. Something like bunny ears 4. And I said 4. We'll go with 4. Okay, so this is our initial call. We're going to step inside here. We're going to ask, is 4 equal to 0? No. So I'm going to hit this return statement where we do 2 plus bunny ears, bunnies, which is 4 currently, minus 1. So it's just 3. Let's step inside this call because I got some code I need to actually execute. We're going to ask, is bunnies, is 3 equal to 0? No. Okay, well, we're going to put more code onto the stack that needs to be executed. We'll do 2 plus bunny ears of 2. We'll step inside this call. We'll ask, is bunnies equal to 0? No. So we're going to return 2 plus bunny ears of bunnies minus 1, or just simply 1. Here is, yet again, more code that I need to execute. I'm going to step inside that call. We're going to ask, is bunnies equal to 0? No. So we're going to hit this return statement where we do 2 plus bunny ears of 0. I'm going to step inside that call, and I'm going to ask, is bunnies equal to 0? In this case, yes. I have hit my base case. And so bunny ears at 0 is equal to a 0. Now I can collapse the call stack. I'm going to start replacing values. I know what this is. It's a 0. I now know what this is. It's 2 plus 0, or 2. I know what this is. It's 2 plus 2, or 4. This is a 6. And lastly, this is ultimately an 8. And that's how that works. So notice that, I can't go back multiple steps in Notepad. So notice that we basically were piling on code until we hit our base case. That is the height of our call stack, at which point we can start solving. We can start collapsing the call stack and finding our final solution. We're going to do more coding back in just a moment, such as Fibonacci. That moment is right now, apparently. So the Fibonacci sequence is a famous bit of mathematics, and it happens to have a recursive definition. So people start to associate these two together. There's lots of recursive mathematics that occurs, Fibonacci being one of them. The first two values in the sequence are 0 and 1, essentially two base cases. Each subsequent value is the sum of the previous two values. So the whole sequence is 0, 1, 1, so on and so forth. We've done the Fibonacci before. We did it using iteration, and we saw that, yeah, we got to start out with two values. Those represent our base cases. Define a recursive Fibonacci n method that returns the nth Fibonacci number, with n equals 0 representing the start of the sequence. Okay, so the base case here should be pretty easy. They're saying that we have 2. We're actually going to see that you can potentially just reduce that to 1 base case. But when n is 0, I'm returning a 0. When n is 1, I'm returning a 1. Those are the first two Fibonacci numbers, right? So we can define those, we can define those as base cases. If n is equal to 0, I'm going to return a 0. Else if n is equal to a 1, I'm going to return a 1. So this is what we meant earlier when we said there's the possibility of multiple base cases. However, take a look at this. Only one of these will actually execute in a given call stack. Because once we hit one of these, we're going to be able to solve everything else, and it's going to cause our call stack to collapse and actually produce a value. So now I'm at the recursive step. If I'm still here, we're past the base cases. We're ready to call Fibonacci again. Okay, well, the Fibonacci sequence itself is just the previous two numbers added together. That is Fibonacci of n minus 1, that's the previous number, plus Fibonacci of n minus 2. What did I do here? Did I spell Fibonacci wrong? Oh, it's, yeah, definitely did it one time. There we go. All right, let's step through this. I'm going to start out with a call. And you'll see why I'm indenting here in just a moment. I'm going to do Fibonacci 3. Okay. We're going to step inside this call and ask, is n equal to 0? No. Is n equal to 1? Nope. So I'm going to return Fibonacci of n minus 1, which is 2, plus Fibonacci of n minus 2, which is 1. Okay. I have skewed this over because what's happening here is that we're forming more of a tree. You have seen all of the examples I've shown you so far of call stacks form just kind of like a slanted stack. Here I have actually two calls going onto the stack at the same time. So it's actually going to form a structure that we call a tree, even though it's upside down. Yeah, that's a computer science joke somewhere in there, or a meme or something. But yes, it's going to form a tree where we actually have stacks kind of branching out, albeit downward. So I don't know what this value is. I don't know what this value is. I'm going to step inside of this function and see what we can find, right? I'm going to ask, is n, which is currently 2, a 0? No. Is it a 1? No. So we are going to hit Fibonacci n minus 1, which is what? 1, plus Fibonacci of n minus 2, which is 0. So I have over here, these two correspond to this one single call. And then these two correspond with this single call. Let's maybe put some more spacing in here. How about like another tab? Am I going to regret that? Maybe. Trying to make visuals in Notepad. All right. So I don't know what either of these things are, right? I can step inside those. I could step inside this one. Kind of pick your poison here. There are multiple things that we actually need to evaluate, and we can't really evaluate anything until we've processed everything. So I'm going to step inside this Fibonacci 1. I could have easily done this one or this one, but we're going to step inside. We're going to ask, is n equal to 0? No. Is n equal to 1? Yes. I've hit a base case. So we're going to actually assign that a value, right? Fibonacci of 1 is 1. I can step inside this call. It's Fibonacci of 0. We'll step inside. We'll ask, is n equal to 0? Yes. Well, I can just simply return 0. Over here, I have this Fibonacci of 1. We can step inside that. We'll ask, is n equal to 0? No. Is n equal to 1? Yes. I actually know the value of that. It's a 1. This is basically the height of my tree. We can start collapsing and solving values. Fibonacci of 1 is 1. Fibonacci of 0 is 0. Fibonacci of 1 over here is a 1. So what I'm left with looks something like this. I actually know what Fibonacci of 2 is. It's 1 plus 0, or just simply 1. And I can finally solve my Fibonacci of 3. It's 1 plus 1, or just simply 2. Okay, so 2 is the third Fibonacci number. I feel like maybe Fibonacci of 3 wasn't deep enough, so I actually think I'm going to do basically that again using Fibonacci of 4. I'm going to tab this over so I can come in and make some branches. We'll step inside this call. We'll ask, is n equal to 0? No. Is n equal to 1? Nope. Okay, so we're going to put two calls on the stack. We'll have Fibonacci of n minus 1, or just simply Fibonacci 3, plus Fibonacci of n minus 2, or Fibonacci of 2. I don't know what these values are, so I'm going to step inside. We're going to do Fibonacci of 3. You could have easily done Fibonacci of 2. Okay. We're going to ask, is n equal to 0? No. Is n equal to 1? No. We're going to have Fibonacci of n minus 1, or just simply 2, plus Fibonacci of n minus 2, or Fibonacci of 1. How about we make it easy on ourselves? Can I do this? Will you bear with me here? Huzzah. Okay. I can choose any of these calls that are on the stack and step inside them. Maybe we'll do this Fibonacci of 2. We're going to ask, is n equal to 0? No. Is n equal to 1? Nope. So we're going to put two calls on the stack. We got fib of n minus 1, or just simply 1, plus fib of n minus 2, or 0. Okay, I have all these calls on the stack. I'm going to maybe choose this one. Fib of 1, we're going to step inside. We'll ask, is n equal to 0? No. Is it 1? Yes. So Fibonacci of 1 is 1. Fibonacci of 0 is going to be 0. Fibonacci of 1. Well, we actually just solved that. It's a 1. And then I can actually figure all of this out, right? I actually can solve for fib 2 on this side, but what would happen over here on the right-hand side is that we'd step inside this call and ask, is 2 equal to 0? Is 2 equal to 1? We're going to put Fibonacci in minus 1 onto the call stack. So fib of 1 plus fib of 0. Notice that this is also occurring over here. Okay, we step inside this, figure out that it is a 1. We step inside here, figure out that it is a 0. This is the height of my tree. This is everything ready to collapse. Fib of 1 is just simply 1. Fib of 0 is just simply 0. Fib of 1 is 1. Fib of 1 is 1. Fib of 0 is 0. So I can get rid of all these things. I can solve fib of 2. It's 1. I can solve fib of 2. It's 1. Oh, that was too much. I can solve fib of 3. It's a 2. And I can finally solve fib of 4. It's a 3. My Fibonacci for the fourth number in the Fibonacci sequence, as long as you start with 0 and 1, is 3. Now, if you were thinking, man, that's a lot, you probably should be thinking that. Because as it turns out, solving Fibonacci recursively, even though the definition is recursive, is quite taxing in terms of processing. Notice that in the example that we just did, we solved several Fibonacci functions more than once, right? Fib of 1, fib of 0, those got solved more than once. Fib of 2, that got solved more than once. And you can imagine that that is only going to increase the higher your Fibonacci number. Whereas what we did with the iterative solution, that was a lot more efficient. That's not the point, right? We did see that putting 2 recursive calls onto the stacks simultaneously formed more of a tree than it does a slanted stack that we've done before. The last thing I want to talk about here, well, second and last thing I want to talk about here, is reducing these double base cases. Realities are, if n equals 0, we return 0. If n equals 1, we return 1. If n equals either of these numbers, you just return n. So we can actually reduce this to say, if n is less than or equal to 1, just return it. Just return what the current number is. Sometimes it's a 0, sometimes that's a 1. The actual last thing I want to talk about here is the fact that we are approaching this base case, right? As long as we are given a positive number, 0 or greater, I should say, a non-negative number, right? Because this is going to start with a non-negative number, and we will approach this base case. However, it is possible to get infinite recursion. If we were to receive a negative number, I guess we would stop with a negative number. We'd be okay there. But we are definitely assuming a non-negative number. If these went the other way, however, right? If this was addition instead of subtraction for whatever reason, we're going to get a stack overflow error. Why? Because my base case is like down here and my call stack is going the other direction, right? We are increasing when I need to decrease towards the base case. So one of our slides said having a base case is not enough, which is true. We have a base case, but I'm not approaching it. In order to actually terminate the call stack, you need to eventually hit the base case. Otherwise, you're going to get infinite recursion and a stack overflow error. Let's recap. In computer science, a function or method is considered recursive if it calls itself, period. Sometimes that can produce infinite recursion, but as long as it does this, it's a recursive method. Any code segment that can be done blank can be done recursively or vice versa. Iteratively, recursion is a substitute for iteration. So far, the examples haven't been great. I'll show you some examples that are kind of why recursion exists, because this is a question that students often have. The stuff that we just did, especially with Fibonacci, seems so convoluted. Why would you have recursion? Well, Fibonacci is not the best example, but there are some good ones. In Java, infinite recursion will produce blank, a stack overflow error. This is a runtime error, meaning there is no syntax that's going to stop you. IntelliJ is not going to warn you that infinite recursion is going to happen. You don't experience it until you actually execute the program. In a recursive method, a segment of code that represents the simplest entity in a problem set and causes the recursive call stack to terminate is known as a base case. You can have multiple base cases, but only one will actually execute in a given call stack. True or false? If a recursive method defines a base case, it will eventually terminate. This is false. As we just saw, the recursive step needs to basically, or recursive call, needs to actually approach that base case. Otherwise, you can still get infinite recursion. So the existence of the base case is not enough. True or false? Recursive methods can define multiple base cases. True. We actually just saw this with Fibonacci, where there was technically 2 base cases. However, only one of them would actually execute. True or false? Only one base case will be executed in a given recursive call stack. This is true. Right? It is what causes the recursive call stack to basically peak and then collapse. In a recursive method, what is the recursive step? Oof. It's basically everything that isn't the base case. And that includes the recursive call. You definitely can find the recursive call inside of the recursive step. True or false? Elements or processes that are added to a stack will be processed or executed in first in, first out order. This is false. This is known as something, this is known as a queue, data structure. You could easily make a queue yourself with like an array list or an array. You probably have like accidentally made a queue where it's just the thing that's at the front of your list is the thing that basically gets processed first. However, in recursion, we form a stack where the last thing to be added is the first to actually be processed. Okay. We are actually going to pause there, and I will pick up in the next video with more coding bat and more recursion. I'll see you then.